Hello, this is Cody Jackson with CodaMom, and we are talking about practical information technology this time, and we are going to be talking about CPUs. Briefly, I just want to give you a timeline of CPU architecture, just for a lot of you who may not know how long the CPU development has proceeded. So the original Intel 4004 CPU was created in 1971. It was 4 bits only, ran less than 1 megahertz, and it had a maximum of 640 bytes of memory. That's not kilobytes, not megabytes, that was 640 bytes. If you're not aware, 8 bits equals 1 byte, so this was really small. 1972, the 8008 Intel processor came out. That was an 8-bit processor at half a megahertz that could handle 16 kilobytes of memory. 2 years later, 1974, the 8080 came out. That was also 8-bit. That ran at 2 megahertz, had a 64 kilobyte memory, sorry. And 2 years after that, 1976, there was a couple of clones that came out. One was the Z80 clone, which was 8-bit as well as the 8080 that it was a clone of. And eventually it ramped up to 20 megahertz, and that was used in the Radio Shack TRS-80 PCs and several others. Also, there was the 6502. That was created by Motorola. That was 8-bit. It was cheaper than the 8080, and therefore it was used in a lot of other computers, such as various Apples, Commodore 64, and even some of the Nintendo products, like the Nintendo Entertainment System. In 1978, the 8086 came out. This was the start of the x86 architecture. If you ever see CPUs listed as x86 or x86-64, this is the original precursor to all of those back in 1978. It had a reduced feature version, the 8088, which was put into the first IBM CPU. And then in 1982, the 286 16-bit came out. 1985, the 386 32-bit. So this is significant because the 386 is still available in a lot of 32-bit software implementations, especially if you're running Linux. You have the choice of going with a 386 or a 686 architecture. 686 was the Pentium Pro that came out in 1995. So the 386 and the 686 are the two main x86 architectures that you will find for operating systems using Intel architecture. And so the 386 is still very significant because that was the first 32-bit CPU. And then later on, we had AMD created the 64-bit extensions, which are now being used widely. But you still do find 32-bit CPUs out there. For example, the ARM processors for Raspberry Pis are still using 32-bit architecture. So these are just some examples of what those CPUs looked like back then. These are all clones of the Intel processors themselves. They come from China, they come from Japan, various other countries and companies that were making them. So this is basically an 8080. This one here is equivalent to a Z80, which was a clone of the 8080. So this is a clone of a clone. This one is equivalent to the 8085, and then this bottom one is equivalent to the 8086. This is just an example of how processors look nowadays. They're square, they're not rectangular anymore, they have a lot more pins. On these ones, these are Celeron, so these are pretty old, but you can see that on the bottom side is a bunch of resistors and surface mount components like that. On the top side is where the actual CPU die is located. So this is the chip itself. This green part is the substrate that's necessary to give access to all of the pins that are on there. Some of these don't have the chip exposed. They have a heat spreader, such as this one or these ones up here, which spreads the heat out over a larger area, and gives a better surface connection for heat sinks. So processor modes, these are important, especially as a programmer, depending on what it is that you want to do. Most programming that you're going to do, high level type programming, you're not really going to worry too much about the different modes because you're just going to let the computer do it for you. But if you're doing low level programming, and depending on the type of processor you're using, you may need to care about, is it real mode, is it protected mode, how much memory do I have available to me, things like that. Because embedded processors are usually very small, very limited instruction sets, and so they may have different modes available to them, especially if it's not a Intel processor. So these different modes came from the Intel 386 and later processors. So this is another reason why the 386 is such an important CPU in terms of the history, because it provided these different modes. Real mode was equivalent to running one of the older computers, the 8086 types. And that only gave you 16-bit instructions and access to 1 megabyte of RAM. It was single tasking, so you could only run one program at a time. If you wanted to run another program, you had to stop your first one and then launch your second one. And there was no memory protection. So if you had programs running, one was paused while the other was running, there was the possibility of overwriting different memory locations and just crashing the entire system. Protected mode, also known as IA32 mode, first came in the Intel 386. It does require 32-bit CPU plus 32-bit operating system and applications. If you don't have any of those, then you're not going to be able to run in pure protected mode. The benefit to that is each of the programs is segregated, meaning that their memory is already allocated to that application, and so you're less likely to have applications overwriting memory of other applications. If a program does crash for any reason, it doesn't take down the entire system. It just kills that one program, but you're still able to use the system. You don't have to do a hard reboot anymore. 64-bit extensions, also known as x86 64, AMD 64, just normal x64, and EM64T, you'll see most commonly x86 64 as the designation, but you may see some of these others depending on the article documentation that you're looking at. So 64-bit extensions were created by AMD, eventually adopted by Intel through a licensing agreement, and that's basically what we see now when we talk about 64-bit CPUs and operating systems. It supports 64-bit software, 32-bit software, and 16-bit software, basically through a type of emulation of those lower bits. 32-bit is actually just IA32 mode, and then there's also IA32E, which allows you to have 32-bit and 64-bit applications running at the same time, or you're just going to be running completely 32-bit via the IA32 mode. True 16-bit mode requires a virtualization environment, a virtual machine or something like that. But it does mean that your CPU is backwards compatible to software that was written in the 70s and the 80s, if you really wanted to do that. The primary difference between 32-bit and 64-bit CPUs is how much memory is able to be accessed and how much data is able to be operated on at a given time. So 32-bit gives you a maximum of 4 gigs RAM maximum and 2 gigs per process. So each application that you're running only has access to 2 gigabytes max. If you have 64-bit, then you are able to have 512 gigabytes of RAM maximum. That's on a motherboard. 4 gigs per 32-bit process, and then 8 terabytes per 64-bit process. We just said that you only have access to 512 gigs of RAM maximum, but using virtual memory, you can get up to 8 terabytes per 64-bit process. The x86 64-bit CPUs gives you 256 terabytes max. That's for that particular brand of CPU, so these Intel compatible CPUs. There are other 64-bit CPUs out there that do not have that 256 terabyte limit. They can go up to 4 petabytes. Some 32-bit operating systems and CPUs are still used. I had mentioned the Raspberry Pi is still using the 32-bit CPUs, and operating systems. Raspbian OS for Raspberry Pi is still 32-bit. For a lot of instances, there's really no reason to upgrade to 64-bit. It just kind of makes the overhead of managing all of that stuff a lot higher without giving you significant return for it. For large file processing and high performance operations, you're going to get 64-bit CPUs, applications, operating systems, simply because they give you access to more memory. You're able to process data quicker because you can access twice as much data versus a 32-bit in the same amount of time. We're going to jump over to cache memory. Cache is basically additional memory that's available to the CPU to store instructions. It uses static RAM versus dynamic RAM. Static RAM uses actual integrated circuits to store the data, whereas dynamic RAM is basically a transistor with a capacitor located next to it, and that capacitor allows it to retain the data as long as power is applied to it. As soon as power is removed from the dynamic RAM, that capacitor discharges, and then therefore that transistor loses its memory. Static RAM doesn't have that problem, and so that it retains its memory after you shut down power. So cache holds the most likely command for the operation that's in progress, and that is why it is so important to have large amounts of cache so that your computer can run as fast as possible. There's a diagram here that shows how this works. So we have a processor, we have the cache, we have memory up here. Normally what happens is the processor is looking for the next operation to or the next command to perform for the operation. So it's going to take a look, and it's going to access the address controller, and the controller is going to either provide a hit or a miss to the processor. If it's a hit, that means that the data is available on the cache, and it only has to go straight from the cache into the processor. If it's a miss, then it has to go all the way over to main memory, and then pull that from there, and then to the processor. And absolute worst case scenario, if it's not in main memory, then it has to go to the virtual memory and pull it off the hard drive and bring it into the processor. Because the cache is so much closer to the processor, it's much quicker to pull data from the cache than it is main memory. This is just a picture of a dual CPU. Up here on the top portion, we have the two CPU cores themselves, and then all of this area down here on the bottom, that's purely for the cache for each of those cores. There's 3 levels of cache. Level 1 is the lowest level. It is closest to the CPU. It used to be on separate chips. Now it's integrated into the actual core where the CPU is. That was what we just saw in the last picture. So each core has its own level 1 cache. Each level 1 cache runs at CPU speed, so whatever the CPU speed is running, that's how fast the cache runs. Normally, the L1 cache is about 256 kilobytes in size and has a hit rate of about 90%. So 90% of the time, the next command for an operation is going to be found in level 1 cache. Level 2 cache is to continue maintaining that performance speed rather than jumping out to main memory. Level 2 cache is going to be looked at next if level 1 has a miss. So level 2 cache also runs at CPU speed. It's about twice the size of level 1 cache. It also has a hit rate of 90%. So between level 1 and level 2 cache, we have about a 99% hit rate of finding the next command in cache instead of going to main memory. Level 3 is found on more modern CPUs, say within the last 10 years or so. Level 3 cache is shared among all of the cores in a multi-core processor, and that's much larger than level 1 and level 2. So we have all the way up to 64 megabytes of shared cache, depending on the processor that you have. It also has a hit rate of 90%. So between all 3 caches, you have a 99.9% chance of finding your next command before you end up having to go to regular memory. So here's some numbers. Assuming you have a 3.6 gigahertz CPU, all 3 of those caches are going to be running at that same speed, and you have an operation that occurs every almost 1/3 of a millisecond, so every 0.28 nanoseconds. We talked about how each one of those caches is 90% likely to have the requested command, and so you put all of those together, you have a 99.9% chance of the next command having been preloaded into the cache. So only 0.1% of the time will your computer have to drop down to whatever the speed is of RAM to get the next command. Otherwise, it's still going to be running at a pure 3.6 gigahertz for the entire time. And so that gives you the benefit of what cache is basically 99.9% of the time you're going to be running at full speed, and only 0.1% of the time are you going to have to drop down to whatever the speed is of your memory. And so that's about it for this video. I didn't want to get really technical into it. This is really just a high-level introduction to how CPUs work, not even looking at what programmers care about CPUs in terms of the registers and the ALU and things like that. This is really just how do processors work, what's the timeline of creation of these, just giving you a feeling of why they're important and how things have changed. We took a look at the timeline of development. We talked about real and protected mode. We looked at 32-bit versus 64-bit processing. And we also had a discussion of cache memory, how it works, and why it's so important. Next time, we are going to talk about the BIOS, or the UEFI. BIOS is the basic input-output system. UEFI is the Universal Extensible Firmware Interface. And those are basically what allow your computer to interact with all of the other devices that are connected to it. I hope you found this interesting. I hope you found it useful. If you have any comments or criticisms or anything, just let us know in the comments and we'll try to address them next time. Thank you. And until next time, have fun, keep learning. Bye.